The last several weeks, we've been looking under the hood at the way our programs interact with the operating system and the hardware. One of the things we've talked a lot about is exceptional control flow of one sort or another. An interrupt that might come from the external world, such as from input on the keyboard, or an exception that happens because your process traps to the operating system for help doing something it can't do itself, or error states such as executing an instruction that results in an arithmetic exception. But there's one more type of exceptional control flow to discuss, and this one can actually result from one process impacting the execution of another. So in today's lecture, we're going to discuss signals, both at the shell level, how to deliver them to a process, and at the code level, how to handle them in your programs. Let's dive into this idea with one more new demystification of something you probably saw very early in COS217. When you've got an infinite loop, press Ctrl-C to break the loop and quit out of the program. Well, now we can start to go lower and say what exactly happens. So when you press Ctrl-C, the keyboard controller raises an interrupt to the CPU. The OS notices the interrupt and handles it, reading in the data from the keyboard and determining what to do with it. Typically, this would be handed over to the process that's currently reading from the keyboard. But in the case of Ctrl-C, it recognizes this is a special command and instead interprets the keyboard input as a request for the OS to make an exception to the normal execution of a running process and indicate to that process some status that needs immediate attention. This OS injection of the notification into a process's normal execution is called a signal. The process, upon receipt of a signal, has either default or custom mechanisms for handling each signal. In the case of Ctrl-C, the notification is signal number 2, sigint. Int here is interrupt, but that's sort of a misnomer because really all of these signals cause an interrupt. And the default behavior here is to terminate the process. That's why it worked in 126 to say Ctrl-C to get rid of a looping program that's running forever. You might have also seen Ctrl-Z. That's the notification of signal number 20, sig tstop, terminal stop. It's the default behavior, again, to stop execution of the process, but instead of terminating it altogether, it puts it in a suspended state until it receives another signal, sig cont. There's a third signal the user at the terminal can send, one you perhaps haven't seen before. Signal 3, sig quit. Unsurprisingly, considering its name, its default handler is also to terminate the process. So here are those steps summarized into a nice bulleted list. Another example of a signal is our old frenemy sig-seg-v, the segmentation fault, which gets raised when we execute an instruction that makes an illegal memory access. Again, the OS gains control of the CPU due to the interrupt. It sends the signal 11 in this case, to the process, and when the process receives the signal, it handles it. The default action for signal 11, as we're all very well aware of by now, is to terminate the process. Generalizing a bit, if process P is executing, if there's an exception, for instance, the keyboard shortcut triggers an interrupt, or memory access triggers a seg fault, or another process traps to the OS to request to send P a signal directly, we'll see that later, the OS will gain control of the CPU to handle the exception, and it will notify the target process, P in this case, of the exceptional condition by sending a signal. This is really just setting a bit among the status bits of process P. Sometime later, P will resume processing. Oftentimes this is actually immediately, as signals typically are notifications that should be handled immediately. So the OS would have good reason to context switch back to P so that it can receive the signal. But whenever it is, the OS notes the status bit for process P, notifies P that the bit was set, then clears the bit and triggers P's signal handler. This might be a custom signal handler for this exception in P. In that case, P will execute the signal handler, which may do all sorts of things, including terminate the process. Otherwise, if there was no custom handler, each signal has a default behavior set by the OS. If P survives the signal, it continues executing as normal after the signal handler completes. So this means you can think of handling a signal, in the case where the process doesn't terminate, as only a temporary step away from normal control flow. Beyond keyboard shortcuts like Control-C and Control-Z and Control-backslash, there are other ways to send signals to a process. One way is the rather severely named kill command, in which you can specify a signal and a process to receive that signal. Despite the command's name, the signal can be any signal, not just sigkill, and the process can be either a process ID or a shell job identifier. Clearly, though, you must own the process that you're trying to send a signal to, or you must be an administrator. For example, oftentimes students leave infinite looping code running on ArmLab, and normally we just send nagging emails to the students to kill off their own jobs, but sometimes an administrator will go in and issue kill commands to do so directly. So how does this kill command work? The kill command itself issues a trap to the OS, because sending a signal is something that requires elevated permissions, so kill has to request that the OS send the signal on its behalf. Similarly, imagine that you began a command that you wanted to run in the background. One option would be to kill it and start over again with the ampersand after the command, but that seems harsh, especially if you've already started. Instead, you could send a sig tstop with Control-Z, then once it's in that suspended state, issue the command bg, which puts the process in the background and sends a sig cont to the suspended process to continue. So again, bg is again just a command that issues a trap to the operating system to send some signals to other processes. There are, of course, a lot more than just the few signals we've seen so far, and we can see all the signals predefined on a system using the same kill command with the -L option. Additionally, the man pages continue to be a fantastic reference. Man 7 signal shows you the disposition, that is the default action, for each of the signals, and it offers additional information about working with signals that's beyond the scope of this lecture or even this course. Continuing with more options to send a signal, a program can send a signal to itself with the raise function call. Frankly, this is a bit odd. One might reasonably question why you would want to send yourself signals. One use, though, is to send yourself signals that have no default meaning or behavior in order to track logic in your program. But to me, this feels like an even worse version of goto in terms of hijacking your program's natural control flow. There is one clever case in the manuals, however, so you can have a look there. It's essentially to have a signal handler to clean up upon receiving the signal, but still end up following the default signal behavior, whatever that might be. A more natural thing is to send a signal to a different process. Much like the kill Unix command, the kill function is a bit overzealously and overspecifically named. It can be used to send any signal to a process, so long as that process is owned by the same user as the program calling kill. As you might expect, I still can't send the signal from my process to yours to terminate your process. That wouldn't be fair, just as it wouldn't be on the shell level. While this certainly can be used to terminate another process you're following, it can also have more mundane uses. Namely, it can serve as a somewhat Spartan form of inter-process communication. For example, an implementation of a heartbeat that indicates to another process that this process has not yet terminated. As we've been talking about signals, I've mentioned the default handler for each of them. So we should talk about signal handlers, which, if raise or signal are analogous to Java's throw for exceptions, signal handlers are analogous to Java's corresponding catch for exceptions. A signal handler is simply the reaction that a program will have to receiving a signal. Every signal has a default reaction. For many of them, it is terminating the process. And if you do man7 signal, you'll get a table of all of the signals and their default actions. These actions might be terminating, it might be ignoring the signal, it might be stopping the process, or it might be continuing the process if it's currently stopped. But a program can install a handler, a function that will run upon receipt of a signal in place of its default behavior. The rationale could be as simple as because it doesn't want to terminate under the condition that it gets a particular signal. But it could also be a means to clean up the state of the process in a more intricate way, such as sending a disconnect message on an open network connection or finalizing a database record. The way that a program can install a signal handler is with the function call signal, which, further lamenting the use of the term kill before, perhaps could have been the name for the function that sends the signal, but it's not. It is instead the function that installs the handler for the signal. Alas, moving on. Signal takes two arguments, the signal that it's installing a handler for, and the function that will be the handler. On success, it returns the old handler. This is convenient because it allows you to save that behavior to reuse if you're alternating between opposite signal handling behavior over the course of your program. Though we can write arbitrary signal handler functions, there are two specially predefined sighandler t values that we should know about, sigdfl and sigign. Sigdfl restores the default handler. Think of this as uninstalling the custom handler, if there is one. Sigign ignores the signal. Think of this as a shortcut so you don't have to bother to write out an empty do-nothing signal, but it's also useful in the context of a signal handler itself to turn off other signals so that if they show up when you are in the middle of processing one signal already, you don't get into a furious spiral of handlers. Before we look at an example, I should also mention that there are some signals that a program may not install a handler to handle. One is signal 19, sigstop, which is used in conjunction with signal 18, sigcont, to suspend and resume a process's execution, respectively. Another signal that cannot be handled is signal 9, sigkill. You may have even heard kill -9 or kill -9 used as a verb, since it's the way the shell can kill off a process and be pretty darn sure that the process will in fact terminate. So now we're ready for an example. First things first, in order to use the signal functions as we've seen here, we'll pound define _GNU source. Piazza Post 530 asked a really great question last week regarding this macro. The short version of the story is that there are various different versions of libraries, including the C standard library. And this is telling the preprocessor which version's header files to import into the top of our program. In this case, the decision impacts signal handling in two ways. It exposes the sighandler T data type in the interface and a few other signal-related function prototypes. Additionally, the different library versions do different things when a primitive, like read or write that we considered last time, is interrupted by a signal. The POSIX standard is to have the primitive fail immediately, which is decisive, but often inconvenient because it results in many checks for that error code, and we all know how easy it is to omit a check like that. Instead, with the GNU source macro, our program will resume the primitive once the handler is complete. Now with that aside, we can just look at the structure of the program. In main, we see a handler for sigint, and the handler is just a function that indicates the signal has been received. The program then prints a message and enters an infinite loop. With the signal handler installed, Control-C will not terminate this program, and will instead print the message over and over again, no matter how many times Control-C is pressed. Other signals, however, are unaffected. We can stop and resume, and we can eventually quit. Here's another example. In this case, instead of only handling sigint, we're going to try to install this handler for every signal. Of course, we know we can't do that. Sigkill and sigstop can't be handled at all. So here we can mash all the keyboard shortcuts we know and still not terminate our program. I in fact had to go to another window and invoke a kill command with kill -9 on the process in order to kill it off. Note also it fails to install 32 and 33, and that's because these are controlled by the native POSIX thread library in the glibc version that we specified in our #define macro, but that's beyond the scope of this lecture in this course. For our third example, let's consider something that's less artificial, one that we might use in practice. This program generates a lot of data and prints it to a temporary log file. However, so as not to waste space on the device, it will then remove the file before finishing the program. What happens to this log file if the user presses Ctrl-C? Pause the video here and take a moment to think about it before moving on to the next slide. When the user types Ctrl-C, the OS sends a sigint to the process. The sigint will terminate the process and thus never get back to the remove call in main. So if we want to be sure that the file will be cleaned up upon exit from the program, unless of course somebody kill9s it, we should install a signal handler. And in that signal handler, we can do the cleanup that we want. So in this file, we have a function cleanup that closes the file descriptor, removes the file, and exits. We install that function as the handler for sigint to avoid the behavior we saw before in which the file would not get removed. Further, to avoid duplicating code, but possibly at the cost of slightly less clear flow of control, we could unconditionally call this function at the end of the program, even if we didn't receive a signal. The last system-level function we're going to talk about is a special system call that asks the operating system to begin a countdown and send the calling process a sig alarm, signal 14, at the end of the countdown. This is a pretty useful function because it allows us to implement timeouts. We can be sure that no matter what code we're about to start executing, we can get back from it in a certain amount of time. Typically, this will be combined with installing a signal handler for sig alarm, because the default disposition for sig alarm is to terminate the process. Let's look at an example. Pause the video here and take a few minutes to reason about what this program will do. In this program, we set a handler for sig alarm. We then invoke the alarm system call to ask to receive a sig alarm from the OS in 2 seconds. It then enters the infinite loop as before. 2 seconds into executing that infinite loop, the OS will send a sig alarm signal, which will be handled by the handler, printing a message. But then instead of exiting, as we saw in previous signal handlers, the handler prints and reinvokes the system call, and then drops out of the function. At this point, the program will continue exactly where it was when it received the signal, sitting in the infinite loop. But because the alarm was reset, in 2 more seconds, the same thing will happen. Handler, print, reinvoke alarm, resume where we left off. This will continue forever, or until terminated by some other signal. Here is another program, our very last sample program of the semester. So that makes it also my very last chance to ask you to pause the video here to consider what this program is going to do. In this program, we set a handler for SIG alarm, and then invoke the alarm system call to ask to receive a SIG alarm from the OS in 5 seconds. This time, instead of an infinite loop, the program prompts the user for input. After the scanf, if we have indeed received the requested information from the user, it cancels the alarm with alarm 0 and confirms the input. But that's if the user enters the input quickly. If, on the other hand, the user doesn't respond for 5 seconds, then the alarm will time out and the sorry message will print. This can prevent a program from sitting around wasting resources while the user is out to lunch or gone for the weekend. And it's pretty nifty, because this is something that our application programs haven't, up until this point, had any way to do. Scanf is blocking, so once we called that function, we previously had no way to advance beyond that instruction. We were at the mercy of the user waiting to return to our flow of control. So that wraps up our last topic of the course, and the last topic for Assignment 7. Specifically, what will allow you to implement the challenge portion of Assignment 7, which is signal handling within your shell. I hope you'll pay close attention to this week's precepts, as frankly, if you take the culminating example from each of them, you're probably 50% of the way towards your final shell implementation without having written a line of your own code. So now we move on to the end game of the course. As we've been stressing these last 3 lectures, Assignment 7 is available. You're able to work with a partner, as has been the case for each of the most recent assignments, and it's due on Dean's Date. If you have a late day left, you can take it, but it'll only buy you until midnight, not the full 24 hours, because of university policies. On the other hand, it doesn't gain you anything to hold on to it either, so you might as well take it to get all the way to midnight. Beyond Dean's Date, the course staff would have to interact with your Res College Dean to make any further accommodations. We'll have extensive office hours over reading period and after Dean's Date heading towards the exam, and we'll have that schedule out this week, announced on Piazza. The exam is in the final stages of logistical review by the university, so I thank you for your patience on those details, and I hope to release them in a full Piazza post with all of the information this week. Finally, study materials for the exam will be posted on the course website, linked from the schedule page. Looking back, this course has been fantastically broad. In the first half, we did a reasonably broad coverage of software engineering fundamentals with our programming in the large lectures. All the while, you were, at the same time, learning C to great depth. And then the entire second half has been a series of parallel downward dives that made up a remarkable amount of material. I hope that you feel good about yourself for having learned so much material, having persevered through a Princeton experience of truly unthinkable circumstances, and I congratulate you for this. I also thank you. This semester has been uniquely challenging, but I've learned a lot and I've had fun. I hope that you can say the same, that you learned a lot and you had fun in spite of the conditions. I hope to see you on Zoom during office hours for the shell and exam prep, and I do hope that Assignment 7 and the final exam go well for you. I wish you all the best.